Good evening. So tonight we will be looking at adding extra functionality uh, to the BIOS, or monitor if you want to call it that. Well, if I can get this to work properly. Where we are here. That's what I want. Cool. So this is one of the books I'm using, 6502 Software Design by Leo J. Scanlon. Archive.org has a copy of it there. At the moment, I'm just borrowing it. It's a lot easier to read from the website than it is off the book. The book is in good condition and it won't fold out nice and flat. So to save the book, we'll just use the website. And let's go to page 114. So it's the mathematics we'll be working on. And I'm just going through and find out which page I need to go to because I've forgotten it. Chapter 5, 115. So which covers quite a few things. So I press here. 110, which is 101. Ooh, the page numbers match. Not often you see that with a book. 2, 3, 4, 5. Right. So mathematical routines. We're not too fussed about integer addition, but we can do multi-byte numbers, which is a interesting one. So what we can do is show how. What's the word here I'm looking for? Bear with me, it's been a long day. How organized I am. So that is at the end, and we can add, so division, multiplication, these are all at location FE0, so that gives us a lot of room to add extra code. RTS. Okay, what we'll do is JSR. Just thinking of this, if we're running low on stack space, we can save a couple of bytes by having all this code in further down. But you guys can't see that, so I'll just bring it into the code and editor. There we go. So this bit is what I'm referring to. Instead of a JSR to the code we're going to be writing today, we can bring it all the way down. But where are we hiding for the rest of the code? Memory test, run basic. So a quick overview of what we've done with basic as well. It is getting to the stage where it's starting to work quite nicely from the monitor. I do have to boot it up by just typing in FF37R, which is the jump routine that this calls here, as the M key doesn't seem to do it sometimes for it. That could be all to do with memory load down being used for other things. And let's get rid of this bit down the bottom here. Alright, so we'll print the basic, we're loading basic, we're checking to see if it's a warm or a cold boot. If it's cold boot, we carry on through, print the cold boot message, clear memory. So this is actually clearing the low and the high of a data value, which I believe basic may be using. It has stopped quite a few issues I was having with it. And then reset all the registers. So resetting the Y register, X register is then being set to set the stack, and then from there we just reset the X register. It's in a known good state. The process is in a known good state. The stack's at the right place. A register, Y register, X register, they're all started off nicely, all 0. And then we can just go to your basic routine. Let's see here. And then if it's a warm boot, we'll just print the warm boot message, reset the stack, and then just jump to the warm boot code at 274, and that's it. And if it does return back from any of those points, it will do a jump to reset, or if it fails for whatever reason, it will do a IRQ process. There's a bit of functionality I want to add into here, which is not this bit here, up here. So at some point we'll want to test if it's an interrupt and process the interrupt. And the interrupts are going to be processed as a, let me see, interrupt table. And I have been thinking about this as well. And that we're using, so you would be loading, I'll just put a bit of code here. So load A from the, we get it from the interrupt priority chip. So int address, and then we transfer A to X. Of course, this will be after we've saved all those registered, and then we would reset that chip. And from there we can do a JSR, and we can use, we may have to add 4 to it. No, I'm thinking of the x86 here for some reason, but the jump table, if it was in 0-page memory, it'd be very easy to jump to it. Because it's not in 0-page memory, it's way up near the top. Would have to do the int address offset X. And then from there it does the rest. So I really only want to save registers in one place, and that's in the IRQ vector processor. And that's why it's called the processor, because it doesn't know if it's doing a break, a non-maskable, or an interrupt. And we would probably do the non-maskable in the same way, and that is have interrupt 0 being the highest one, and that would be going straight to the like an AND gate or something, straight to it to say yes, this is the non-maskable interrupt, and it triggers that way instead of triggering the normal interrupt. But that's not what we're here for today. It's just a little bit of a distraction. Now we scroll all the way back up to, okay, maybe not, lost in my own code. At one point I will have to get to at one point I will need to break this all down into smaller blocks, as I've already done with the floppy disk controller side of things, which is something to look forward to in the future. This is the Kim load save, that's just from basic, and macros. This is all some of the stuff I've done outside of streaming, and that is just our street print message macro. Save registers, that's a work in progress. I'm not too sure if that's going to work. These two here will definitely work. They do definitely work. The break macro is just there so I can add breakpoints to debug parts of the code. It's not an easy way to debug, but it does work in a way, because then it just brings it back into the monitor, and I can examine what those registers were at the time of the break. Right. First things first is we will be doing the one we just saw, new math functions. And one of the things I need to do is, where is that? Software design. I've only got it for an hour for this one here. So if I bring the browser back in and move it to the right, can I zoom out? No. And then bring that works. Alright, and then I can move it more to the right. Okay. I'm just messing with Windows at the moment, window location, so we can do this, and I'll bring that to the left. All right. Nope, I broke it. Alright, so what does MP add do? Well, it's multi-precision adding. So, oh, don't play, don't do, be nice. Alright. Okay. So, as you can see, two multi-byte numbers, one starting at location 21, the other starting at location 51. The result replaces the number in that start location 21, and the byte count is contained in location 20. So there are 3 locations we need. Now, because we've already got a lot of data at those initial, what are they called? Page 0 locations, this will trash a lot of other memory location at page 0. So, how well is this going to work outside of page 0? That we can try out today. MP add. So MP add, and we'll load accumulator. Now this first one is the fetch byte. Careful. Broken it. Nope. Nope. Alright. Alright. So, starting at location 21, the other starting at location 51. So that can imply that it's 30 bytes in size for each of those. Both of them are 30 bytes. So, starting location is 21. Ending location is going to be 50, yeah, and then from 51 to 71 bytes. So we cannot use 100 because that is where our stack is. So stacks from 100 to 1FF. 200 is the start of the monitor characters, but we can start at say 221, and hopefully not get into trouble with the characters that are at that location. Alright, let's see here. Cool. So we're going to add so byte count, and that's going to be at location 0220, and MPADD, and then it's going to be A MPPADD, D, that's going to be B. B. O251. No, O221. And okay, so that's the locations there. So we fetch the first things first is we fetch the byte count, and byte count, and then we load the index. Of course, it is going to be, oh, that doesn't need that, 0, 0, and then we clear our carry. Next byte, we load the first accumulator, load accumulator at location 21, comma, X, so that's the first 8 bits. And then we add of carry the 51, which is the second location. Offset those bits as well. And we STA back into 21. The result now, the thing to do is to think about what it is actually doing and how it is actually doing this. If I can draw a little diagram, we'll do it here. So, and do a third one. Okay, so there'll be a carry flag, and that is set in the processor if two numbers have that carry. So if we're adding F and adding F, there's a carry flag, and that's 1. So the next time that add is done, it also includes that carry flag. So if it was 3, it would add that 1 to it before, as I'll show you here. So this is A, and this is B. Alright, and the results down through here. And we'll do it in binary. And the result is going to be, of course, 1, 2, 3, 4, and then the carry flag is going to be set. If this bit here is all zeros, if I do it this way, this is going to be a bit easier to do. Okay, so actually I did say FF, so if we do okay, so that's the first byte, and then on the second byte both of them are not FF, they are, okay, so the first one is 0, 0, FF, the second one is 0, 1, FF. Okay, and then with the carry flag, So the first time it's through, they're both added there, and there's a carry which sets that to there. Alright, so that's for this first block, this first 8. That 8 and that 8 added together. Then the second bit, which are these ones here, because that carry flag is already set, it is a set, essentially, you could think of it as that being already added to that bit there. So there's 3 values being added, and that just results in, let's see here, so that's essentially what it's going to be in the end, using that carry flag, because it's addition with carry. Right. So if you remember that if you are doing an addition with carry, if you don't need that carry to start off with, it's been set, it can make a mess of your addition if you're only looking at an 8-bit value, not a 16-bit value or more, as these all work out to be. Let's see here. So I'll get rid of that. Hopefully that was clear. Alright, so store the outputs, and then we're going on to the next byte. So increment the X, which is your counter. The counter is your X counter, and your decrement Y. Y was used as fetch byte count. Okay, so Y is used as your byte count. So if your byte count is set to 4, you're moving down to your 3rd byte, your 2nd byte, your 1st byte, and your 0 byte. And next one is break not equal. Missed it. P and E. Backs to NXT byte. This is why I like editors, as they work. And RTS, of course. RTS is return to subroutine. Alright. Very easy to program, and there's a little bit more we can read about it as well. This has been going for 22 minutes. I've probably got about 40 minutes left in the burrow. About 10:29. Where's the time? Yeah, 40 minutes. Alright, integer subtraction. And so again, this is using the same addresses. So 51 to 21, and the byte counters location in 20. Okay, so if that's the case, we will actually just leave it like that to make things a lot clearer of what's going on. So MP sub JSR MP sub and no, don't need that. RTS, and we want to do, because it is an FE function, so again we've got MP sub, and we've got a byte count, which again we're going to store in location 2202220. I always put the leading 0 to reduce ambiguity out, to make it easier to understand. That way, if you do see it as 220, is it... Of course it's 220, but I like to make sure. MP sub A, MP sub B, and again we'll go with the convention of 0221, and MP, the B is at the same location. And first things first is we do load Y with our byte count. And we load the X with our value 00. And we set carry. Is it set carry? SEC, subtractive carry. We set carry. So subtraction, we set the carry flag. Alright. NXT bytes. Subtract, add. Okay, so of course it's going to be different. Because if we've got... Essentially it's what I've shown you previously, but in reverse. If the carry bit is set, then we subtract the 1 from it. So do I want to explain it? Could take a while to set up. So it's essentially same as before, but in reverse. I'm going to leave it at that. So load accumulator to location 21, and we were 21 as MP sub A, comma X, and S subtractive carry 51. No, it's not 51. B, comma X, and it's, then we store A, the result back into A at location X, which is the offset. Increment X, INX, and decrement Y. And if Y is now 0, we travel to the next NEXT underscore. Oh, how did I spell it? NEXT. NXT. Byte subtract. And return to. I was going to say return to sender. It's not. It's return to subroutine. Alright, so that's the add and the subtract. Now, the subtract and add use the subtract and add that the processor has. The processor does not have a multiplication or addition. Technically it does not have multiplication or addition. Multiplication or division, sorry. You can do division by doing a shift left or shift right. I cannot remember which one it is. And you can do the multiplication by a shift left or a shift right as well. All depending on which way round the whether it's a big Indian or little Indian as well. And so depending on which way around it work to do a multiplication by shifting. But it's usually times 16 though. That's the problem. Was it times 16 or times 2? Times 2. Times 2 for each of them, sorry. So every time you shift left for little Indian, it is times 2. Going the other way, it's division. But take that with a grain of salt because it could be wrong. So, in the book, nope. Alright, I'm going to maximize that so I can see it and find the right page. There we go. Nope. Okay, integer multiplication. I'm not going to touch base with all this bit through here. Let's just go straight to the code. Okay, so start product and counts 8. Shift multiplier right into carry. Carry equals 1. Yes, click carry. Product equals product multiplicand. Alright, back in a second. Alright, don't worry about the background noises, it's just stuff falling on the ground. Addition and subtraction are a lot easier to understand, so the easiest way to understand the code is just to go through the code. And sometimes you can get that wrong too. So unsigned means just that, it's unsigned. So these are all positive numbers, they will not go negative. So let's change that to MLT8 to show where it's come from. So this is the multiply 8-bit. Okay, so first is what do we got here? So we've got so that first location is 21, which is the multiplicand, so we'll just call it A. And again, we're storing that in 0, 2, 2, 1, and then MLT8 underscore B is going to be stored in string, no it's not string, hex 022 20. Okay, so 20 20 and so MLT 8 underscore R result is going to be stored in locations 0, 2, 2, 2, and that is going to be L. I'm just going to put this here just for convention, or not convention, just to be say pedantic, but it's just to be clear on what's going on. Senate is returning a 16-byte number. Alright. Now to the code. It's MLT8. So first things first is load the accumulator with our a number. So it's here is clear the most significant byte of product and multiply bit counter equals 8. So we'll be decrementing X at some point. And it's a immediate number. So NXT byte and underscore M. So left shift LSR, left shift rotate, or is it just left shift? Logical shift right. So LSR is logical shift right. So we're shifting it right by one. Okay, so and that is from location 20. So for 20 for us was number B. So be careful when we're doing this, because we could get this a little bit mixed up. And BCC, break, carry, clear. I'm not sure if it's carry clear or something else. BCC is branch on carry clear. Break branch 8. Now I'm adding extra parts there. That way, extra bits onto our keywords here. So I've added MLT8 align. They've got a line here. That way, if anywhere else in the program, if I want to put a line, I can put a line and not confuse it with an align somewhere else. That way, when the compiler decides to compile it, it will be compiling it so it knows it can be jumped either 127 behind, 126 behind, and 127 ahead of its current location. And if it sees another align somewhere, it goes, okay, how do I jump to that? I don't know what I'm doing. Throw my hands up in the air and complain about it. Add of carry, so this is string 21, which is MLT8 A. Okay, so this is the MLT align part. So what is actually happening when we're aligning it? It's a good question. Okay, so Logical shift right A. Now, A doesn't have a number, but the register is at logical, shift product right. And it's shift product right by 1. Does it test to see if there's a carry? No. Now this is the famous ORO, rotate right, which is broken on pre-76, 77 chips, which is do not use on pre-77 chips. 22, which is so shift product right. So that's the first time it's adding anything into the second one, the low byte. Okay, that's interesting. Okay, we add that to the low byte, which is result low, decrement x, and break not equal. So if it's not equal, x is not equal to 0, so it's hasn't gone through it 8 times for 8 bits for each bit. We then go to next byte m. We could also put m out of T8 next byte. That might have been an easy way to do it. Store A into the top half. Result high and RTS. Alright. I sort of have a rough idea what's going on, but I'm gonna have to come back to you on that one to figure out how it actually works. Now the last one is double precision multiplication. Do I want to add that at the moment? Subroutine multiplies. I'm going to bring that over for you guys to read as well. There we go. 8-bit signed. Signed as well. Ooh, negative and positive numbers. Let's not worry about that one. And that's 16-bit by 16-bit. Worry about 8 bits for now. And then I'm surprised they don't do the signed one. Might be a trivial thing to do. Might be something interesting I could do as well. Integer division. Dividing unsigned numbers. Another thing we could do is seeing how long this would actually take. It's working on a bit by bit basis, and you can clearly see that up here. That number there, I wish I could highlight it, divided by that number equals something, that number. Okay. We'll leave those for another night. It's starting to get a bit long with the tooth. So which also give me a chance to read through it and understand it a little bit more for next time. Right, let's get rid of that. So get rid of the browser, keep the editor up, and bring the editor up in full. Nope. Oh, I know what's doing that. It's because I have the editor over one page. Cool, I'm happy with that. Right, so what we'll do now is burn an EEPROM or compile it. See if there's... I better get the terminology right. We shall assemble it, find errors such as 815, syntax error, so out of carry and that there, and 870, that's not defined, so what did we call it? MP add. And we'll just call it by its correct name. And okay, 819, next byte is not defined. Which is a Coop. So it compiles and we load it. I'm not showing the loading and the compilation and the burning. It is just tedious EEPROM write to program. I mean, tedious. Assemble the program, write the EEPROM, verify the EEPROM, place EEPROM into the, I was going to say into the bin, and go from there. Okay, so at the moment we are going to test 3 functions for this processor. Oh, for the BIOS. So let's boot her up. At location, I do feel like I'm going to be writing it over. Yeah, okay. At 220, I got 20 bytes, 32 characters to do this in. I've already used 4. Okay, so what numbers do we want to add together? First of all, we need to know how many bytes we're going to be using. And if I had a pen, it would be nice. Okay, so at 220, we're going to say use 4 bytes. And okay, so that's at 21. And then at 251 we do that. So the result will be in 220, and it will be the last one here, showing what data that we've added 1 to 0. Just bring up putty because we haven't brought that up. And we're not in basics, so that's location 220. We're doing 04, 1, 2, 3, 4. Okay, so that's all good, and then we can just go 220.22f. So that's our data, and then at 251 we add 00000001. Cool. And then we call I don't even know what address that is. Let's go find out in our list. The monitor listing, it's reloaded, and bring that across. So FF05. Okay, and then it we should see the result. Okay, so that hopefully is the result at. Alright, you guys missed that. Oh, I'm going to do it that side as well. So let's move that over there. So we've set the memory at 220, including the byte count. Number of bytes to get it for 251. We're going to call FF05 and run it from there, and the result will be at 221, and it will be those numbers there. I hope I've got that right as in my noggin. 68N error. That should not have printed error for some reason, because I'm not in BASIC. Oh, right, FE. FE05, because FF05 printed that. I don't know. I don't know what I did. Right. Okay, so let's check the let's check the data. No, let's not check the data. FE05. Let's just run it. 20. I may have stuffed up there. Alright. 220.22f. Alright. And we got 2f there. That's because we made a mistake and put 2f into 21. Okay, so let's start again. Let's check to see where that result should be. Subtraction, subroutine. The result replaces the number that starts in location 21. Okay, so location 21. So again, 0, 4, 0. Cool. And cool. And 0, 1 of that one there. And we're calling and apparently the byte is returned starting at location 21. So okay, what happens if I add 250 dot 255 251 0 1 251 we get 0 1 0 0 0 0 0 0 and 0 0. Now if we called fe05 and run it from there, and 221 dot 22 if why well, we can see that it's run because no, we haven't. Okay, so that's interesting because that actually is needed, that X, and when I went to compile it, okay, so we were missing a part of the instruction. Okay, so which is easily done, but I may have entered it wrong the first time. The assembler complained that it was wrong. I've removed it and didn't check to see how it was wrong, and assumed it was correct after I took it out. So this time we should see the add with carry work properly. Let's see here. Bring that up. Cool. Let's start again. So 220 04 00 00 00 00 251. We enter in 00 00 00 01, and we do fe05r. Gives us that. Results in 221. So in 221 we should see nothing. You're kidding me, right? How disappointing. What have I done wrong? Let's try. Let's try that. Let's try. In 220, we've got your 4 bytes plus 1 in that one there, and A's that up. It's down. B, C, D. Interesting. That was the arrow keys I was pressing. Alright, so 220, we'll load it with 04, 01, 00, 00, 00, 00, 00. Cool. And in 251 we will load 01 and the rest of the zeros. Cool. And FF0, no. FE05 R does that, and then okay, it's not what I was expecting. Okay, let's have a look at the code here. Okay. Oh. Oh. Ay, caramba. Quite a classic. I cocked up. Of course it's not working. And there's nobody in chat to tell me I was doing something wrong. Okay, so going over it, I made a mistake. No excuses. I made a mistake. I should have known better. I made a mistake. I'm not even going to be blaming that I'm tired. That's just wrong. All right, that's burnt. All right, go number 3 or 4. I can't remember. Let's try this again. So let's turn the processor on. We don't need to load BASIC. We don't need to load the Intel code. I think I've disabled the Intel code. And let's try the initial one, which was that 0. That's 0. And that's 1. Right. Because that'll give us, I'll do 5 there. Yeah, so that makes it a little bit more readable. Okay, so 220, we load 4 bytes, 00, 00, 00, and 220222F. Okay, so that's that loaded to 5 0. Okay, and then we 250.25F. We can see that's all zeroed up. Now we do FE05R. We don't want to do that because that's the wrong address. So FE05R 20, and then we go 220.22F, and we should see at that location there, it's going to highlight everything, that location there, we will get that number we want. And F me, it did not effing work. Uh, 251 dot 25F. Okay. It disappeared, didn't it? Not just disappeared. Did I not enter the data? And oh, okay. So it added 0 to 0. That's why it didn't work. 250. Okay. This time, that's the fourth location. FE05R 221.22F. It works. Okay. Okay, so if I add A to that, it should be B. So if we do 251, no, that'll be A0, A1. A1. Now, let's try this. 251. Actually, let's do this. 0251. 25F. It's A0 again, like we added last time. And FE0R, nope, FE05R. And we go 221.22F. It's 41, which is okay, because I want to try to get it to overflow to the left. Grow from, yep. So we can do a couple of times. I'm gonna do another time. That didn't work, did it? It didn't go to the right. Unless it grows to the left. Let's try this. 251 dots. No, 251. Okay, so 250. 221. So FE05R. Now, what do you think's going to happen? Is it going to be FF and the rest of it's moved over to the right? Yep, FF, everything is moved over to the right. So it grows from left to right. Let's just check that though. Something all of a sudden didn't feel right. One FE. So 1 FE. Yep, 1 FE. Interesting. If you have your calculator out, you add FF and you do plus FF and then you do your equals, you got 1 FE, 2 FD, 3 FC, 4 FB, 5 FA, 6 F9, so the last letter is counting down. The right hand one is counting down. I'll bring calculator. I never even noticed that before. What we'll do, where's my OBS? PDF browser, emulator. And we haven't got emulator there, so we will find calculator. And calculator. Okay. Show you what I mean. FF plus FF equals. Watch that number, the first one. Watch the last one. See how the front one 5 counts up, but the last number counts down. Alright. The second number now counts down too. Alright, now what about the third number? This time, because it's rolled over, it'll still count up. Oops, I may have screwed up. Yeah, I screwed up. That's right. Let's not get distracted anymore. So that was the add. And the next one is... See, I'm running out of time. I'm going to do this pretty quickly. Is the subtract one, and where's my thing? And if I do 2F1 dot 25F that there. Now, if we subtract one from the other, we should get back FF, and subtract is at location. Ooh, yep. Modified because we broke it. MP sub FE09. Oh, gotta bring you guys back in here for the editor. No, emulator. Putty. There we go. Alright. 11:15 my place, so I really want to finish this up. FE09. So that should be the subtraction, and we will see in 251.25F, we should still see FF. 221.22F, we will see FE01. Oh yeah, FE01 is that FE, yep, that works still. And I can just do that again, bring it back down to if we do v09r221.22 f back to if. So that's pretty cool. We could do this in BASIC as well, but I'm adding the functionality to the BIOS, which is going to be for the next part of it as well, when we're starting to mess with floppy disks and other ways of importing basic programs in. Let's see, multiply. Okay, so this is 8-bit numbers, so in 221 and 220, so I've got two numbers, 4 and f. And if I was to do multiply, we are FE01 and in 22 and 23 we've got our results, and there's no division, so it's all good. So 22.223 is FC0, which is 03 FC. And we can do that by 4 times so 03 FC. You got to read it in reverse because of the way the processor is orientated. So that's our math functions for tonight. A little bit of a distraction with the calculator, a little bit of a distraction with mistakes, and let's see, the other thing we could do is actually just remove those and put them in their own file so I don't get lost in the code. At this stage, I'm just going to leave it in all in one file and go from there. So that's it for tonight. See ya. Bye. Well, it's not see you bye. I'm just going to stay here a bit longer, but do no talking and do just some work. So I'll leave you to watch if you want, and leave you to it.